Does this work? I hope so. Sorry, it takes a moment. Too many things which go through the cloud seemingly. Hi, everybody. So how we get started? So morning session is always a little bit, well, you need more coffee. Let's put it this way. We get going. So I would like to tell you a little bit about what I think about AI-enabled robotics. And this comes also a little bit from the background that in this place Intrinsic, which is a new part of Google, actually robotics, we are actually interested in trying to take robots to really reliable applications out in the world. And the big question is always, so how do you go? And a simple way to get started is like in research, we use prototypes. We get going, we basically build them quick and dirty. We want to basically write a paper, we want to get a first result. But then there is a fair amount of work how to go from a prototype to something which is actually becoming something which is much more practical, much more reliable. And the question is actually how hard is it and what you have to do? And also think what this workshop is about, how much can you actually use machine learning and AI topics in order to get there? So what do we really want? In the end, what we would love to accomplish in robotics at some point is synthetic intelligence. We want to make all kind of little robots work automatically and do useful things in the world. And this can be tiny nano robots, it can be big robots like humanoid robots or robot arms or whatever your favorite robot is. In the end, we would love to get to these kind of systems which behave autonomously, intelligently by themselves. What is behind this is always, in some sense, the same thing. You need to perceive the world, you have to create actions, and you have to adapt. And what is actually really important, and I know many of you know this inside out, but it's good to not forget, this happens in a loop. These are closed loop systems, and closed loop systems are unfriendly because they can go unstable. They can do all kinds of terrible things and destroy the world around you or themselves. And I will come back to this repeatedly. This closed loop nature is really important. And getting actually learning into these loops and then actually have learning never stops. Everybody stops their learning algorithms, okay? Everybody cheats. Nobody ever lets them run forever after. It's not true. Some people do it, but very few do it. Since everybody is worried about, oh, it's going to be out of distribution. This is the latest word, okay? This is such an annoying word, but it's out of distribution. It will basically overfit. It will, God knows what it's doing. So there is an old classic way of doing things, adaptive control, where people knew how to control these things and do it perfectly, but that also doesn't scale to the systems that people would like to control these days. But again, I come back to this a little bit more. So what are robots? It's super simple in some sense. So you connect essentially a robot with sensors to your control box, and you have actuators which you actuate in order to get back to the environment. Super simple thing. And again, so exciting. This is the most primitive effect I've ever done. Physics matters. It is about physics. You cannot cheat physics, okay? Don't even try, it's not working. And performance in physical system matters as well. And again, this is really great. Everybody sits here. Now, 90% performance in many machine learning algorithms. Great, accomplished something, it's really cool. If you guys stand out of your chair and 1 out of 10 times you fall on the ground, you will be weeded out by Darwin very early on, okay? You will not survive. Physical systems have very different constraints, how to survive and what makes them work. And of course now, in this new world, we would love to get some kind of machine learning, AI is the new word, into this control box, since that's really all what it is. Processing the sensors is some kind of information processing. Getting out actuator signals is a policy, it's some form of information processing. Now, how do we do this? Now, what we really want, and this is now going to the topic of the workshop, we would like to get some reliability in these systems. And I just put up what people in, this comes actually out of, I think, NASA originally, but has been adopted in many industries. So what are actually the kind of levels that you need to accomplish in order to be good? And there's initially this kind of orange areas. This is just getting started with basic concepts and fooling around and playing a little bit. This kind of light blue area is this you build prototypes in the labs. And this is pretty much so, I think 3 to 4 to 5, sometimes to 6 is mostly what happens in research labs. And this is nice. It gets you going. You get something which looks kind of okay. And then you have to officially make the jump to the dark blue area. This is the higher technology rarity levels. And they actually become hard. And actually the jump from 6 to 7 is not just 1 up. It feels more like 10 to 20 up before you get really to something which you can take out into the real world and make it work there. And it's reliable. It's a miserable amount of work. The interesting thing is actually sometimes you have to change your approach entirely. What you've been doing before in your prototypes, which kind of got you to some level of performance, that may not ever get you to the level of performance you want to accomplish in a practical world if you really want to have a working system. And I think Jin Lan mentioned the example from Boston Dynamics. It took them a miserably long way to get into the blue area. And Mark Rayburn can basically overemphasize that's not enough, what it took. And here's my complaint, essentially. It's great to have learning curves, which people publish all the time, all with confidence bars, even it's really cool. So what? Okay, it got better. So you were not entirely miserable in what you've been doing. But getting better is really not good enough. Again, the example of getting out of your chair. You need to get to some higher level of performance. And for physical systems, 99% and higher is actually not so uncommon. All of you guys, they're pretty good at doing your dishwasher, okay? You're cleaning it out. How many things do you throw down on a daily basis? Nothing. You get it done. I don't say you have to do it one shot. You can retry and then do error recoveries, but you get it done 100%. So this is kind of what we should try to get it. So what has been happening in the recent years, I think, in robotics is also kind of fun. Obviously, there is this new world now, artificial intelligence and big data. Here, the typical transformer model, some pictures from Google DeepMind Robotics on trash sorting. This is really the new thing where there is some new machinery which seems to work surprisingly well. It needs a lot of data, and how do you make it work? But also, how do you make it reliable and to be figured out? Other things which have happened simultaneously is, of course, we have new sensors. I'm not sure you still remember, but when the Kinect sensor came out, the first time roboticists had a 3D sensor, which was really nice. And now we get increasingly more sensors and cooler sensors and cameras which can see transparent objects and all kinds of things, which is nice. And we got compute. TPUs, so in Google, there's all these beautiful TPUs. They're actually nice. They're like an aquarium of TPUs. They're jellyfish and viperfish and what are they all called? Pufferfish. They have all kinds of silly names, but they compute really well. So they are fantastic in order to actually compute these big models. And another thing which is, I think, up and coming, this is also a little bit where Intrinsic, where IAM tries to help, but equally like Ross before, this is general robotics platforms which actually encompass and allow you to use all those things at the same time. This is really towards AI-enabled robotics. And unfortunately, there's a lot of infrastructure occasionally. It's really annoying. And everybody who's been working on robotics, now, how much time do you spend before you actually get something done on your robot, which is worthwhile doing? Usually, you spend months before you have your robot set up and it does something useful. So this is kind of the world in which we're getting, and then see what we can do there. So let me, nevertheless, get a little bit into some basic ideas and foundations. And I'm starting, okay, I'm starting more bottom up, okay? I'm not starting saying, hey, let's do everything with foundation models. I would like to look a little bit on what does it take to make things actually reliable on a smaller scale. And, well, what do you need for robotics? You need control, perception, you need some skill learning, you need usually also multiple robot coordination. One arm is often not quite enough. And then there's very boring topics like safety, but at some point, if you want to get out in the real world, you may actually worry about your robot falling on a little child and then this child is squished, okay? That's not fun. So you need to do something about that as well. I just use a fun example, which we've been exercising for the last few years. This is kind of the world of insertion tasks. It's obviously, in some sense, boring, but it's also something which you as little children, you learn that early on. You put your little blocks together and you feel really cool. And with 2 years, you can actually do this quite proficiently. And then later on, maybe we plug in USB connectors in our computers and it works or it doesn't work, depending how bent this thing is. The National Institute of Standards and Technology put out these NIST boards, which you might have seen. These are just kind of abstracted industrial tasks towards the research community, so that's more fun to play with. And also, just a little reminder, most people, in the end, when you get started in robotics, you think in terms of state machines. There's nothing else you can do You could try to avoid it. We will talk about this. But in the end, you create a sequence of components. Often these little circles are some primitives. The primitives can be machine learned or whatsoever. And of course, you can have a state machine which basically just abstracts everything in the middle to one big, whatever policy state, which you learned magically end to end. This is also possible. But this concept is quite valid, and it's good to think about it. All right. So robot control, I will not bore you a lot with this. This will take too long. But in the end, there's something like real-time control, and you got to do it right. If you don't do it right, your robot will misbehave. And then you usually, what most people machine learning like, they have some kind of a non-real-time layer which has to communicate into the real-time layer. And again, that is possible to do this right as well. You should not forget that this is actually important. It is really the basic what makes your robot work. Without that, I can tell you, I cannot debug your robot, not at all. Then it's just nonsense happening there. And there's equations, impedance controllers, and all these kind of things. I know nobody likes them, but they're actually not very hard, and they're very easy to use in the end if you do this right. Just for fun, is my video running? Yes, it does. So this is a silly little robot trying to plug in lots of connectors on a kind of made up, what we call cable monster setup. And the good thing is it doesn't use any AI and machine learning and perception. It just basically knows roughly where those sockets are and where the connectors are. And then basically use a little trick. It basically goes in with an edge of the connector first, and then pushes against the sides and then slides in. The environment is totally capable of guiding the robot to do the right thing. All of you know how to do this. You get up in the middle of the night, you fumble around to find your light switch or whatsoever. We can do this kind of guidance from the environment quite nicely. And this works, this is just purely quote unquote impedance control mechanical intelligence. Why not do it this way if it works? I just try to keep this out as a reminder. So let's put it this way. And what we're doing at Intrinsic, at least, we don't shoot with huge cannons on little sparrows to get started with. We usually start, what is the baseline? What do we need in order to do more if it's not good enough? For instance, you can now add perception. Of course, people have now been using deep learning for visual perception in robotics for quite a while. Nothing very new. And you can actually do fun little things, also more in the last inch domain rather than big end-to-end things. So this is here actually the same robot again, trying to learn some other connector insertion. This is actually a data connector, which has extreme high friction and very low tolerances. And you have to really insert it the right way to get started. And the robot is just poking around. This is basically a scripted schedule where it fools around. It's a self-supervised learning to learn about how does the world look like if I'm missing that socket. And after you've practiced this for 2 hours, you can actually learn a nice deep learning post-correction model, where initially this is now faked. Basically, the robot gets initially a huge error up to a centimeter, how to approach the socket, and then looks at it and says, oh, I'm wrong, and I'm correcting it. So tiny, minuscule, little last inch learning just for what matters. We don't learn free space motion, okay? Free space motion is super boring, sorry. You don't have to learn that. And then if people even wiggle around spastically for free space motion, this is also not good. So I rather focus on what matters. It's one concept on how to get actually performance. And that gets to really high performance. Now, do I make any progress with my slides anymore? Don't know. Okay, manipulation skills in general. Coming to this graph. So people use obviously standard kind of directed graphs, behavior trees, there's all kinds of concepts. And the interesting thing is in these little circles, you could actually learn more complicated behaviors. I mentioned that before, like for instance, complete control policies. And just showing you, and still use the rest of the state machine as the basic idea, like pick something up, do the transport in free space. Don't worry about learning these things which don't matter. So the blue lines and the blue nodes are more what would be interesting. And this is actually some work from Jin Lan's work actually over the last years. And let me see, let this going. This is using just a very nice mixture of learning from demonstration, variable coding, and reinforcement learning, and very data efficient reinforcement learning. And this is Jin Lan's magic hands, actually. He can operate a space mouse, but this is accelerated, so he's not that fast, but he can do this amazingly well. And what the robot has to learn is how to insert a little transformer on this PC board, which has to be very gently done, and you have to do some gentle corrections to make it work. And then after the first kind of initial trials, the robot learned, basically the demonstrations, then it starts poking around terribly. you should actually see the pain a little bit over time. Okay, it's poking and poking and poking, but the nice thing is it actually gets better really fast. So all these things are essentially learning tasks which were learned within tens of minutes, or not hours or days or God knows what. And this all on local compute power. And then in the end, actually, this system learned how to do this. These things are actually not easy to insert. Some of them have really tiny little feet, and you have to really wiggle them into the right spot. On the right side, I'm not showing this video, don't have enough time. Actually, Jin Lan did recently also some work where this was done only with touch perception. That means for stroke sensing at the wrist. And on the right side is doing the same thing with cameras, works even better and nicer. A simple, small, last-inch learning approach for what matters. The rest, who cares? Picking up, grasping, transporting, you don't need this. But this goes to reliability of essentially 100%. We haven't tested it on tens of thousands of trials, but it is really amazingly good. And that becomes actually feasible to actually do in the real world. I also would consider this a benchmark for many other big models that people try to learn. Now, this is super data efficient and fast to learn. Now, is that then worth at some point to collect whatever, how many 10,000 or millions or whatsoever trajectories for training a big foundation model, and will it outperform what this thing can do? And we don't know that yet, but it will be interesting. All right, let's get to the next slide. Come on. All right. Just some other fun component. All of this was done now with a single arm. At some point, you need to coordinate multiple robots. And that big dual arm robotics, I think you'll see the Yaloa setup outside. That is already a path to go there. But why not just use 4 robots or 8 robots? There's no limitations that you have. And this is just a little bit of a teaser. So these things have been usually done with motion planning algorithms and search algorithms. This is together with actually Matt Lay and John Schultz from DeepMind London. And we've been working on some systems which actually learn these things completely with reinforcement learning. So the robot, basically the learning system just gets a robot work cell. And it's, in this case, supposed to learn how to service 40 weld points on that silly structure and learn automatically which robot takes care of which weld point and how to basically create collision-free paths, how to get there. So this is a little bit of a teaser. This is going to be a paper in the near future. But this is actually now completely reinforcement learned. There's no other search structure being imposed anymore. And what is even more fun is, this is just in sim so far. You cannot just, this has come from spot welding, a typical multi-robot application in industry. But you can also start assembling things. That means you have dynamically created objects in collision geometry, which you have to take into account. And it becomes a system which is only limited essentially by the fantasy which you have, how to feed it data. Am I doing time-wise? Oops. Okay. So let me move to the last topic very quickly. Safety. I'm not going to tell you a lot about safety. I'm not an expert about this. But most safety is usually done that there's some components which are model-based analytical methods, how to make a robot safe. What people would love to accomplish is number 6 at some point, that you learn safety critical components. And this has yet not been done. And this is a big, complicated topic by itself. I'm not going to touch on that, but it's really important at some point if you want to get a robot out to do something. So quick summary. So I super much care about 3 components: algorithms, data, and infrastructure. You have to create the right infrastructure software in order to make this work. You have to create algorithms, and you have to be data-driven if you use machine learning and do these things right. And you should try to use the best of all of them. So no conviction that you just one thing to rule them all, okay? It's not the Lord of the Rings. It is actually robotics out in the real world. It's a system, and you should use the best you can find from everything. And there's this interesting question about last inch versus long horizon approaches and modularity and primitives. I personally love primitives. I've worked a lot of kind of motion primitives in the past. And what is the right structure which you can actually impose here? But the big question, of course, generative AI is going to rule it all. Maybe. But it's definitely an interesting domain. So the large language models obviously have been making huge success. And in robotics, people now talk about vision language action models. So this kind of the big kind of robotics transformer ideas, that they can do something. And fine, you basically learn latent models. In the VLAs, you at some point hopefully learn about physics here, my topic, which I love, but I don't know whether they learn about physics efficiently. And at some point, you actually hope, well, that similar large language models can learn from the internet. Can we actually create automatically a huge amount of robotics data where something similar can be learned? And that becomes now increasingly more complicated. I think you've seen some of the RTX, the robotic transformers from Google, as an attempt to bring together 50, 60 groups to provide data for a big learning model. But they're still in the infancies. They have to still get better. And what we actually intrinsically are interested in is actually creating data at much bigger scale, since we have a platform for robotics which can create much more data. One thing which, of course, works is like with large language models that you can actually create, for instance, these kind of state machines automatically. So this is a sketch. This is just made up. But we actually had an intern working on this for the last 3-4 months, and she could do something similar like this within 3 months without any problems using GPT-4 as a background. And you could then, with a dialogue, start refining and putting reinforcement learning systems in there. So this is just a nice vision, which we hope that we can get it. But this is not so hard. The nice thing is that gets actually into the long horizon tasks and the task planning, which is nice. But inside the boxes, I still use my little term primitives or my short horizon or last inch things. And that's kind of the approach which I hope will be a little bit more practical and successful, at least in the near term. So coming to an end. So I really care about using algorithms, data, and infrastructure for physical systems and how to make this work. And foundation models are clearly on the verge, and we have to see what comes out of that. But it's a little bit premature whether they can conquer physics. And there's one thing. Can you give me a compelling machine learning approach which has basically revolutionized physics, the same as what the revolutions we've had in computer vision or natural language processing? And so far, physics does not play with you. You cannot overrule physics with software and machine learning. The physics underneath will always be your worst judge and will basically bring you back to Earth. And it will be very interesting what the foundation model world and the new AI world will bring. Thank you very much.
So, any questions from the audience? We probably have, Emma.
Great talk, Stefan. What were you actually learning and how are you learning it? Like, are you tweaking some primitive or PD control?
Okay, now, in which context?
In the insertion thing where you said you do a little bit of learning at the end.
What Jin landed essentially this kind of assembly.
Yeah.
You want to answer this question? It is your word. No, it's using learning twist policies essentially, and impedance policies, which are given to the robot. So it's streaming. It's about 10, 15 hertz streaming data, which is then interpolated into real time at a kilohertz frequency. But he's the expert. Okay, he can explain it all. I was actually on time, which is amazing.
More questions from the audience? We can have maybe 2 or 3 more. 2 more.
Thank you for the talk. I had a question about the same work, the insertion work. I was curious if you guys are assuming that the grasp, like the relative orientation between the object and the gripper, is fixed in all of these demonstrations, or whether that's something that you are reasoning over as well.
So the grasp is not accurate, let's put it this way. So it doesn't have to be sub-millimeter precision how to grasp. All these errors were nicely compensated by the policy afterwards. But there's essentially a basic grasp pose where you pick it up. But none of these robots are sub-millimeter accurate anyways. And you will always get stiction effects and some perception effects. You need to go to the basic grasp point first. There will always be an error accumulation.
But if it was, say, like 90 degrees off?
If we're 90 degrees off, then So I wouldn't normally, well, you could learn this, obviously, if you learn now a complete grasping system. We usually use a pose estimator to get starting with this, or we assume we know roughly where the system is. It can be compensated with, it can be compensated completely with machine learning, but there's also really nice pose estimation techniques if it's a rigid object, which is not so complicated.
Any more questions from the audience?
Thank you for the talk. I have a question about the last example you gave about using language to interact with the system building a computer motherboard. I was wondering, it's very interesting to see that it can do this long horizon planning, but do you think that this has given us the right level of abstraction? Because it seems like building a motherboard is a pretty known task, and there's not really that much need of adjustments using language.
It depends, to be honest. This is an example, and this is just an illustrative example. And it goes essentially to this entire topic, code as policy, that people have been exploring, particularly in Google DeepMind Robotics in a couple of papers. You can definitely argue there's other things which are more interesting if you have less structured tasks where you put things together. I was just primarily interested in, can you actually automatically generate these state machines? And actually, can you generate also parameterization for these state machines? Each of these nodes in the end has some open parameters most of the time. And they have to come from somewhere. And sometimes you have to refine them. So sometimes you have to say, oh, can you basically push down on the board a little bit with more force or with less force? Or can you wiggle a little bit more in the z-axis in order to get it in? So there is some room for a dialogue. It can be more profound than other tasks, no doubt about that. But it's not entirely trivial to get it done. This is the fun thing. It looks like, oh yeah, this is just straightforward assembly. It's not. The moment you do context-rich assembly, it's not that easy anymore. Since you have to basically argue and reason about contact forces, and that is actually where if-then rules completely fail, since that becomes a mess.
Thank you.
We can probably take one short questions.
You should set up in the meantime.
Yeah. But if not, we are actually on time. Let's give Stefan a round of applause.